All right, in this section we're going to continue our talk about statistics, but we're going to be applying some of those ideas to probability distribution. So we've been using statistics to describe symmetrical and skewed distributions of data. Today we're going to talk about how to construct a distribution that involves probability, and then we're going to use statistics to analyze that distribution. So the vocabulary that you need to be on the lookout for are these different phrases and words. Make sure at the end of the video that you can explain what all of those are. So we're going to start with constructing a probability distribution. Remember from past classes that a sample space is the set of all possible outcomes in a distribution. And there are two kinds of distributions that we can talk about. We can talk about discrete distributions. Make sure you write that on your note guide. And continuous. The sum of two dice distribution is a discrete distribution. Why? Because if I roll two dice, I can get a sum of 2. So if I get a 1 on each die, then I would have a sum of 2. I can get a 1 and a 2, or a 2 and a 1, and I can get a sum of 3. I can roll 2 2s, a 1 and a 3, or a 3 and a 1, and get 4, and so on. But I can't get values in between. There's no way for me to roll 2 dice and get a sum of 2.5, for example. So this is discrete because it's countable. Whereas miles per gallon, this would be a continuous distribution because I can take on, it can be 18 miles. Well, this axis is probably gallons and then miles. Whoops, sorry, would be the other way. But both gallons and miles, I can do fractions of those, right? I can use 18 gallons of gas, I can use 18.1 gallons of gas, I can use 18.2. I can take on any value from 18 to 30 here, but in a discrete distribution, I can only take on here the values 2 through 12 and nothing in between. So the value of a random variable is the numerical outcome of a random event. A random variable can either be discrete or continuous, like we just talked about. Discrete means countable, I can count it. Continuous is it can take on any value, so it would be impossible to count how many values it could take on. So take a look at this first example. Find the random variable and classify it as discrete or continuous. So here we have the number of hits for the players of a baseball team. The random variable here, which we're just calling x for now, is the number of hits. That's what we don't know, right? That can change. That's our variable. It is finite and countable, so we say that it is discrete. I can easily count how many hits a player has. They can't have 1.785 hits. They can hit it once or twice or 3 times or 4 times and so on. All right, part B, same idea. The distances traveled by the tee shots in a golf tournament. So here when we're talking about distance, that's going to be our random variable. The distance is what's changing, and it can take on any value. I can go 20 feet, 20.5 feet, 20.575 feet, right? Distance is continuous, so here my random variable is continuous. All right, I want you guys to try this one, same idea. All right, the answer here is B, the number of automobiles sold in a given week. This is discrete because it can be counted. The number of automobiles would be my random variable x. It's finite and countable, so it is discrete. All right, a probability distribution for a random variable is a function that maps the sample space to the probabilities. So it's like my domain is the sample space. What are the different outcomes that can happen? And then the probabilities are like my range. And we can do these with tables, equations, and graphs. We're going to be focusing in this section on discrete probability distributions and not continuous ones, okay? So the domain, again, is the sample space. What are the possible outcomes? The range is the probabilities of those outcomes. I can do probability distributions in 2 ways, and we're going to talk about both theoretical and experimental. It can be discrete or continuous. We're going to be focusing on discrete. Remember that each probability has to be between 0 and 1. It could be 0, it can equal 0, and it can equal 1, but probabilities can't be larger than 1 because 1 means 100% chance. And the sum of all of the probabilities must equal 1. So we're going to talk first about theoretical probability distribution. Theoretical probability is based on what is expected to happen. So the best way to understand this is with an example. If I flip a coin, there are two outcomes. I have a probability of 1/2 for flipping a head, right? Because there's one head out of two sides of the coin, and a probability of 1/2 for flipping tails. So notice the probability of getting a tail and a head are both 1/2. If I do 1/2 plus 1/2, I get 1. So this probability distribution, I know, includes all of the possible probabilities for flipping a coin. That's what this last one means when it says that the sum of the probabilities has to equal 1. All right, let's take a look at this example. We have a stack of cards numbered 1 through 8. So I have 8 different cards that I have in my stack, and our random variable x is the sum of any 2 cards that I draw from that stack. Notice it also says with replacement, so that means I'm going to draw a card and then put it back before I draw my second card. So it would be possible for me to draw 2 8s or 2 2s or 2 1s or whatever. So I'm imagining that I'm going to draw a card 1 through 8, and then I'm going to draw another card 1 through 8. So there are 64 total possible outcomes, 8 times 8. To determine the relative frequency or the probability of each outcome, I divide the frequency by 64. So there are 64 total combos, if we want to think about it that way. But some of them can happen more than once. So here, how can I get a sum of 2? That only happens if I draw a 1 and then I draw a 1 again. So that's one possibility, one combo out of 64 total combos. How can I get a 3? Well, that only happens if I draw a 1 and a 2 or a 2 and then a 1, right? Because the order is different. So that's like 2 out of 64, which reduces to 1 out of 32. How can I get a 4? Same idea, 1 plus 3, 3 plus 1, or 2 plus 2. So that would be 3 out of 64. So I want you to pause the video, take a second to make sure you understand how they got each of those relative frequencies. These are theoretical frequencies. We're not actually drawing over and over and over. We're just assuming based on probability how often it would happen. Now if I graph this situation, this is what my probability distribution would look like. Again, notice that my domain here is the sample space, all of the possible outcomes. So the smallest sum I can have is 2. The biggest sum I can have is 16, and I can add up to all those numbers in between. And then on the left-hand side, it's showing the probabilities. Here they have them as decimals. So remember, the probability of getting a sum of 2 was 1 out of 64. So that was 0.01 something. And they have that graphed here. So this side, the y-axis is probabilities. The x-axis is the outcomes. Notice that this is a discrete distribution because I can have a sum of 2 or of 3, but there's no way for me to draw cards and get a sum of 2.6, for example. All right, so that was theoretical probability. Experimental probability comes from actual experimentation, so it's real data that we gather. We often use a simulation to construct these. You guys did these in 9th grade when you did some probability simulations and you took the probabilities, the experimental probability based on that. So we actually observe the frequency and then we get the probability from what we see, not from what we think should happen. So let's take a look at this example. It's the same idea, the stack of cards numbered 1 through 8 with replacement. And I'm not actually obviously going to have you do the trials right now, but we're going to draw 2 cards 64 times, or we could use a random number generator to do that as well, and complete a tally sheet. So let me show you what they did here. Basically what you do with experimental probability is you actually do the experiment. So you draw 2 cards, and let's say that we got a sum of 3, so I make a mark here, I got a sum of 3. I draw 2 more cards, let's say I got a sum of 11, I make a mark there. So I do this 64 times, which is what they asked me to do, and I just tally up how many times I actually see what happened. And this is the relative frequencies that I get. So here are the frequencies, right? I got a 2 once, I got a 3 3 times, I got a 4 6 times, I got a 5 5 times, and so on. And then I divide each of those frequencies. Remember, relative frequency is the frequency divided by the number of trials. So this was 1 over 64, 3 over 64, 6 over 64, and so on. So that's what my probability distribution frequency table looks like. And then if I were to graph it, notice this graph looks a little bit different than the graph that we did for the theoretical probability. The theoretical is what we assume would happen based on probability. This is what actually happened in my experiment with 64 trials. There's something called the law of large numbers that this section talks about. Basically, it means if I were to do more and more trials, here we only did 64 trials. If I were to do it over and over and over, the more times I do it, the closer my experimental probability would get to my theoretical probability, right? The larger the amount of trials, the closer it gets to the theoretical. All right, analyzing probability distributions, last part of this section. The two most common statistics that we use to analyze discrete probability distributions are the mean, or the expected value, and standard deviation. Expected value is something you did in 9th grade. It's the weighted average of the variable. So the way that we get the expected value is to find the sum of the products of every possible value of x. So I take what x could be, or the outcome, and I multiply it by its probability. Oops. And then I add up all of those. So I take the outcome times the probability, and I add them all together, and that gives me my expected value. Hopefully that rings a bell from 9th grade. So let's take a look at how we would calculate expected value. Here we have a tetrahedral die, so 4-sided, 1, 2, 3, 4. Find the expected value if I roll the die one time. So in a 4-sided die, 1, 2, 3, and 4 each have a 25% chance of being rolled. So remember, this sigma means the sum of adding things up. So what's the chance of getting, there's my outcome. What's the chance of getting a 1? There's the probability, 1/4 or 0.25. What's the chance of getting a 2? 1/4 or 0.25. What's the chance of getting a 3? So notice I'm taking each outcome times its probability and adding them all together. So my expected value is 2.5. So I would expect generally to roll a 2.5, although that doesn't really make a lot of sense in this context since it is a die that we're rolling, but that would be my expected value. And that can help people when they're designing experiments or designing things that involve probability to make good predictions or assignments of values like you guys did in 9th grade. All right, try this one. Find the expected value for this situation. All right, your answer here should have been B, which is $1.88. All right, here's the work for this. Of course, hopefully you noticed that you were missing the probabilities for each outcome. So these are the outcomes, my prizes, right? I can get a $10 prize, a $25 prize, a $50 prize, a $100 prize, or a $250 prize. I need the probability for each one. So I take the number of tickets that get that prize out of the total. So the probability of getting a $10 prize is 100 tickets out of 2,000 tickets, which is 1/20. The probability of getting a $25 prize is 50 over 2,000, and so on. So notice my work up here. I took an outcome. So here's my $10 times its probability, 1/20. $25 times its probability, 1/40th, and so on. I add them all together and I get 1.875, which rounded to dollars and cents is about $1.88. All right, last part of this chapter. If the expected values don't give me enough information, let's say the expected values in two distributions are really close together, then we use the standard deviation to get more insight. We have talked previously about how to get the standard deviation. Remember, for each value, we subtract the mean and square it. And then I get the mean of those and get the... Okay, I'm better now. Basically, we'll be reviewing the formula for standard deviation that we used before. We're getting the mean of the square of the differences and taking the square root to get the standard deviation. So if I were to do standard deviation in this situation, we don't have a ton of time to show it. We can finish going over it tomorrow, but if I look at my expected values, the expected value of a ticket would be -50 cents. Sorry, this keeps moving on me and I'm not sure. And here they're showing you how they got the standard deviation. We'll talk more about that